Hi everybody, my name is Ryan Hollister, and today I'm here to present to you a refined photogrammetry workflow that consistently creates high-resolution virtual 3D models of geologic specimens that can be then shared on Sketchfab. I collaborated on this project this summer with Curtis Burmeister, Scott Georges, and Nicholas Warner. So photogrammetry, if you're unfamiliar, is basically the process of taking a whole bunch of images of an object from different angles and having a computer triangulate where those pictures were taken from in space, and are able to create a three-dimensional model from that we can then overlay photographic textures on top of to make it look like a real object. So for me, I've always loved rocks as a subject sample here. So the very first one I ever made was a lava bomb back in 2016, and you can tell it suffered from a hide-a-key syndrome, where it had an empty hollow bottom, and it looks like you could hide your old spare house key underneath. But now we have enough technology and improvement in our workflow to create these really neat high-resolution solid models that allow both quantitative and qualitative analysis. So I think that's a pretty big advancement. So the new workflow that I'm presenting today kind of arose from the need of Curtis Burmeister needing his beautiful hand-carved wooden models here turned into virtual models for his virtual field camp exercises that got pushed online due to COVID this summer. So the scanned models needed to have exceptional resolution for his planned quantitative applications. But after I tried making these models the first time, I realized that the large depth of field and the range of that depth of field made capturing an entirely in-focus model really difficult. So I had to come up with a new plan. So in order to make a model of any kind in photogrammetry, you need some basic supplies. The first supply is a light box or a photo tent. You need a black background, or you can use white as well, but I prefer black. You need a bunch of small lights in the foreground with some battery-powered USB cords on the side. You also need some large panel LEDs that really cast a big amount of light. You need a turntable that has a felt covering on top of it, and it can be an automatic turntable or a manual. Mine is manual. You need a really good camera that has at least 24 megapixels of resolution. Mine has 45. And then on my 24 to 70 millimeter lens there, I have a circular polarizer on the end that really cuts down and reduces glare at the bottom. And then you need a really strong tripod. And my most important invention I've ever made, I think, is this black spandex hairband that I've stuffed with my son's kinetic modeling sand, kinetic sand, that acts as a nice base to hold all of your models as it's rotating around. It molds to it and holds it steady in place, which is pretty cool. You also need a very strong computer that has a fast GPU and a fast CPU. And the great thing is graphics cards have just had a revolution this month, and they're dropping in price. They're almost half as much for cards that are now nearly twice the speed of some of the best ones on the market currently. So as with all things photographic, lighting can make you or break you. So I always take my big panel LEDs and kind of shine it in from the side, so it makes a diffuse like sunlight, but it's still angled at the specimen just a little bit. And then I use the small lights in the foreground to cancel out any shadows from those big lights. They're app controlled, so you can really have a high degree of control of how your light is being cast. So when you take the images themselves, capture them in the raw format, and by having them in the raw format, you can process them later on. You want to make sure that you're in the manual mode so that every single image you take has the exact same settings, because when you process them later on in Lightroom, it makes it really easy and fast to process them all at once if everything is the same to begin with. So ISO of 200 or lower, which gives you a really fine grain, so you can zoom in really far without getting too fuzzy. And then the aperture anywhere between f10 and f14, because that's kind of the sweet spot of the crispness and the sharpness of most lenses. And then you'll have to set your focus, your shutter speed basically is going to be dependent on how much light is in that light box. So you can use your light meter to figure out what you need to do to get the proper exposure. So the big desire here is to capture a whole bunch of images of the entire object from all sorts of different angles, so we can trick the computer into thinking we've made a complete sphere around this object that it can then stitch together. The way I've done this is that turntable model. So I always end up putting my specimen on the turntable, and the first 36 photos that I take are with the camera kind of at the horizontal level, face on to that specimen, and I rotate the specimen 10 degrees between each shot and take the image So basically 36 times around for that 360 degrees. Then you raise the camera up just a little bit, like 30 degrees or so, and you take another 36 images, and then another, put the camera up at about 30 or 50 degrees, and take another 36 images as it spins round. So in order to prevent that hide a key phenomenon, you have to expose all the different surfaces of that object. So after you've taken the first 3 sets of camera positions, I always take my specimen and then flip it up on one of its other axes and repeat the process. So 36 images at horizontal, 36 images at 30 degrees, and then another 36 images at 50 degrees. And then you flip it over to the next part and repeat the process. So it'll give you about 324 total photographs. So kind of the bane of the existence of 3D models so far when we've created these have been this texture smear, and it kind of destroys the reality that this is a real rock, right? It makes it look like it's not so real. So to prevent this texture surface, or to prevent this smear from happening, you basically need to have multiple images of those objects in focus from different angles. And so it's really difficult to do when you have a very large specimen or a specimen with a big depth of field. It's hard to get every single object completely in focus every single time. So that led to some brainstorming. How could I capture several focused images of every surface on a specimen? And then how could I trick Metashape into using only those highly focused portions? So that's where I came up with this focus selected double masking process. And what's really cool is it uses Photoshop to eliminate the backgrounds in the images first to make that's basically what Metashape will use to build the model. And then it also uses Photoshop to create a secondary mask that can then be loaded into Metashape that includes only the most focused pixels, and we use that mask to build the texture. So we use one mask to create the model, and then another mask to completely create that really high resolution focused texture. So if you have a model that's a nice wood block that's large and has smooth surfaces, you can use a method to capture the images called the focus select. And then if you have kind of bumpy images or bumpy specimens like you see over there that are intricate or maybe macroscopic, you want to use macro lenses, you can use a process called focal stacking, and that will take a series of images and make them into one highly focused image. So in the focus select method, basically what you do is you have to manually select, when you take each picture, manually select each area and try to capture a plane that is perpendicular to the camera lens. And then as you rotate the image, try to alternate between near field things that are in focus and then far field places that are in focus on that object. And hopefully by the time you've taken 300 images or so, you have multiple images of every single area on that model that are in focus, hopefully at least 3 or 4 that can then be used later on. So that's the focus select. The focus stacking method then uses your cameras. Most of the new cameras have onboard focal stacking, which basically slightly shifts the focus ring between each picture and adjusts the depth of field that the camera is taking a picture of. And if you set the camera for like 15 images, you can then take those 15 images and put them into focus stacking software like you see on the bottom here, and it aligns all the focus parts of the images and combines them into one composite image that is completely focused. So that's really crucial for capturing like sub-millimeter detail. So before we move into Metashape, we got to take these images and post-process them. So we'll take those images and we'll color correct them first. So we usually import them into Lightroom, adjust the white balance, remove chromatic aberrations, adjust the shadows and highlights and things like that. And then you can copy the settings from one photo and paste them to the rest of your photos in your library, and it will adjust everything all at once, so you don't have to do it manually over and over and over again. When that's done, save these files as JPEG images, and then we can import those into Photoshop. If you did the focus stacking method, you take those JPEGs that you've just exported for Lightroom, and then you have them pieced together and made into the composite single images, and use those single images to then go into Photoshop. So when we get to Photoshop, the first thing that we need to do is remove the background of this and the specimen stands, and that's going to help Metashape later on construct a really good selection of the specimen to create a good model. So you can use this by using the subject select in Photoshop and then deleting everything else that's not the subject. And then the second step is in that same object that's open, the same picture that was open, we're going to use something called the focus select or the focus area select in Photoshop. And what's really cool about this, and this is the golden ticket here, is that you can mask out everything that's not in focus, and you can mess around with the sliders to choose exactly the style that you're looking for there and what's in focus, what you consider to be in focus. And then it applies a mask that then gets saved to what we call an alpha channel, which is invisible to you, but Metashape is going to call on it to make a mask a little bit later on. And then you have to save these images as a JPEG 2000 or a JPF format, which is a relatively small file size, but still maintains this alpha channel, which we can use as a mask later on. So then the last thing you need to do in Photoshop is just choose one picture, delete the actual subject, make the whole thing black, and we're going to save this as the background so that Metashape can pretend that this is the background it's looking for, and it can exclude everything that's black when it creates the models in Metashape. So here's the general Metashape workflow that I'm going to go over right now. So the first thing we need to do is import the background masks in Metashape. So you import all your images, you drag all of them into Metashape, and then you import the background mask, which now is telling Metashape to ignore that black background, and everything that's not black is the subject that we're going to use to make the model. So once it knows how to do that, you go to Workflow, align the photos, and that'll do its first bit to make this nice, what we call a sparse cloud, point cloud here. So what's really cool about this, and Dexter Perkins showed me this last year, you can use this model gradual selection tool within Metashape to basically throw out and select and throw out some junk points if points are not aligned correctly. So you can select them, delete them, and then once you've done that, you can go to the tools, optimize cameras, and it really zones in your cameras to make sure they're all in the right position to create what we call this dense point cloud. So you go to Workflow, build dense point cloud, and then I would also choose calculate point confidence, because after you build this dense point cloud, you can then set a threshold. And if you, for some reason, have points that are not necessarily exactly where they should be on your model, you can filter them out, select them, delete them, and then if you hit reset filter, you'll have a nice dense point cloud to which you can then build your mesh. So once you build your mesh, you're basically connecting all the dots with triangular faces from your dense point cloud. Then we need to import the masks of the focus masks to overlay onto here so that we can create the really highly focused images. So where you do this is you go to File, Import Masks, and then you choose that alpha channel that's been saved in the file. You say you want to replace all the masks that already exist, apply it to all the cameras, and then it creates a mask of only the most focused images. So from that, we can then move to building our texture, which is to me like applying paper mache over an object. And I like thinking of the images as the paper mache that you're just slathering on top and it makes an image after they're all stuck together. And so this is like the least understood part of Metashape, and I don't still understand it 100% clearly, but basically the texture size is in pixels. It's kind of like a square pixel size. And then the count is the number of squares of each one of those pieces of paper mache, basically. How many pieces of paper mache are you going to put on there, and how big is it? And off to the side here, you can see for the approximate megapixels that it produces. So I would not go above 8,000 for each one of those for most computers because it can't handle it. But you can play and experiment with those different variables to see what you come up with. So the last thing you need to do after the model is created, you upload it to Sketchfab, and then you get some really good results. And you can upload it to Sketchfab using the onboard uploader that is included in Metashape. So you get some really awesome results, but what are the teaching applications? Well, we can quantify this block topography, and that enables instructors to ask quantitatively meaningful questions. So Scott and Nick have been working on taking some of these models and doing some really neat things with them, like making geologic maps and digital elevation models. And then Kurt has also taken some of these pseudo-ortho photos at the beginning and has made a bunch of topographic map exercises for his field camps. So last thing I want to say is all of these rocks and specimens, they thrive when they have a sense of place. So I'd always geotag every specimen you have if it comes from the field. And it's also really useful to put in virtual tours as well. So here are our resources. Please contact us and connect with us on Twitter and Instagram. And I hope you enjoyed this. Thank you.